Welcome to The Explainer. We've taken a 3.5-hour masterclass on learning physics and boiled it down to just a few minutes. And today, forget about memorizing formulas for a second because we're going to talk about a whole new attitude for tackling science.
So let's just dive right in. You know that sinking feeling you get in a science class? You miss one lecture, maybe two, and suddenly you're staring at this massive backlog. Every new class just piles another concept on top of stuff you haven't even wrapped your head around yet. It's a super common anxiety, especially when you make that jump to a more competitive level.
So how do you actually break out of that spiral? Well, the lecturer we're looking at today argues that the solution isn't just, studying harder or pulling a bunch of all-nighters. The most important lesson isn't a formula at all. It's about adopting a completely different way of thinking.
And he offers some pretty surprising advice. When a student asks, "Sir, what is angular momentum?" his answer is, "Kado hota hai," which literally means, it's a pumpkin. A pumpkin? What's he talking about? Well, his point is that when you run into a big, scary, complex term for the very first time, don't panic. Just call it a pumpkin. It's nothing. It's just a word for now, and you'll figure it out later.
This is what he calls the Kado method, and it's super simple. Step 1, stop asking what is it for every single new thing. Step 2, just focus on the formula you're given, work with it. And step 3, and this is crucial, trust the process. Trust that you're going to learn the deep why behind angular momentum or torque later on, when you've got more context. It's like building a foundation before you try to understand the whole skyscraper.
Okay, so armed with our new "it's a pumpkin" attitude, let's take a look at how physics is actually built. Like in any game, you have to learn what the pieces are before you can even start to play. And in physics, these pieces are the fundamental building blocks of the entire universe.
These basic pieces are called physical quantities, and it's a really simple idea. A physical quantity is just any property of something that you can measure. That's it. Your height, the speed of a car, the temperature outside, yep, all physical quantities. This is the language we use to describe everything from a simple ball rolling down a hill to a rocket blasting off into space.
Now here's the beautiful part. There are literally thousands of these quantities, but they all fall into just two simple buckets. First, you've got your 7 fundamental quantities. Think of them like the primary colors. They're totally independent and aren't made from anything else. And then you have the derived quantities, which is, well, everything else. And every single one of them is just a combination of those original 7.
And here they are, the magnificent 7. Length, mass, time, temperature, electric current, amount of substance, and luminous intensity. That is it. This is the entire alphabet of physics. Every single formula, every law, every complicated concept you will ever run into is just written using different combinations of these 7 letters.
So, okay, we've got our alphabet. But an alphabet is pretty useless if we don't all agree on what the words mean, right? We need a shared language of measurement. That's where units and dimensions come in, to make sure that when I say something, you know exactly what I'm talking about.
The lecturer has this fantastic example. He says, if I tell you I have 100 biga of land, you probably have no idea how much that is. And why not? Because a biga in one part of India is a totally different size than a biga somewhere else. Without a standard international unit, like a meter, our communication just falls apart. It's meaningless.
And this need for a standard language brings us to the whole idea of dimensions. Now, don't let the word scare you. Dimensions are just the basic recipe for any physical quantity. They show you exactly which fundamental ingredients like mass, length, and time are used to make it, and we just use symbols like m, l, and t to write it down.
Let's make this super real with an example. Let's take velocity. We all know the basic formula. It's distance divided by time. So, in our new language of dimensions, distance is a length, or L, and time is, well, time, or t. So the dimensional formula for velocity is just L divided by t, which we write as Lt to the minus 1. See? That's the recipe for velocity.
So what's the big deal? Why are we going through all this? Because this, right here, is where our pumpkin attitude really starts to pay off. This new language gives us an incredibly powerful tool to check our work. A golden rule in physics that lets you see if things make sense even when you're dealing with pumpkins you don't fully get yet. It's called the principle of homogeneity.
And the rule itself is unbelievably simple. It's basically common sense. You can only add or subtract things that are alike. I mean, you can add 5 kilograms and 2 kilograms, no problem. But you can't add 5 kilograms in 2 seconds, right? It makes no sense. In physics, that just means you can only add or subtract things that have the exact same dimensions.
Okay, let's put this rule to the test. Imagine someone gives you this equation, V equals A times T plus B.
All you know is that v is velocity, which has dimensions lt to the minus 1, and t is time, with dimensions t. Now, that plus sign, that's our big clue. Because of our rule, if the left side of the equation is velocity, then every single term being added on the right side must also have the dimensions of velocity.
So, that first term over there, a times t, what do its dimensions have to be? Come on, it's not a trick question. The whole term has to match velocity, so its dimensions have to be L, t to the minus 1.
And check this out. That lets us solve for the dimensions of that unknown a. If the dimensions of a times t equals L t to the minus 1, then with a tiny bit of algebra we can see that a must have the dimensions L t to the minus 2, which, hey, you might recognize those. Those are the dimensions of acceleration.
So what about that other mystery term, b? Well, since b is being added to other things that have the dimensions of velocity, it has to have the dimensions of velocity, Lt to the minus 1. How cool is that? We just figured out the physical nature of a and b without knowing anything about the specific physics, just by using pure logic.
All right, let's just quickly recap the main takeaways here. First, your attitude is everything. How you approach learning is way more important than what you just memorize. Second, all of physics, the whole shebang, is built from just 7 fundamental quantities. And finally, dimensions aren't just some abstract idea. They are a powerful tool you can use to check your work and make sure your equations actually make sense.
And that really brings us to the final question this whole philosophy raises. Is physics about cramming your head full of facts and formulas? Or is it about learning a powerful new way to think, a new framework for analyzing the entire world around you?